Okay. Now it's not. I'll tell you what page it is. It's a different page. I'll tell you in a little bit. Whoops. Okay. Do you want to write the title down? Don't worry. You don't need your book just yet. You just need paper for the moment. Oh, I wrote too big. Calculating uncertainty. Now, this is something you perhaps did with Lorraine when you did your chemistry labs. Does this sound familiar, this word? Uncertainty? No, never heard of it before. Ken? No? Chow? No? Matt? Really? Are you sure? Okay. I believe you, I guess. So, are you sure you didn't have it? Maybe Lorraine called it a different word, like maybe error.
Yeah.
Calculating error. You did these calculations with her. Yeah, okay. So look, this is the problem. So the problem is often we want to know a true value, I'll call it mu, from a sample of measurements. So, for example, here's a very simple example. You want to know somebody's height. So to try to be accurate, maybe you measure their height 3 times. So maybe it's like 1.8101, and then it's 1.8102, and then it's 1.8095 or whatever. Okay. So, is any of these the true answer? No. I mean, maybe, maybe not. We don't know. We want to try and know what the true answer is. So we imagine that when we make a measurement, we have our estimate. So for example, what value would you use here? Now I know you did questions like this with Lorraine where you had to measure the temperature or something like that. Would you use this value, this value, this value, or something else? Yeah, what's the something else? The average, yeah. So the best estimate is equal to the average. Okay? That's one thing. And then the second thing is that the estimate has an error. So is the average going to be exactly right? No. It'd be nice if it was, but it's not. And we call that error the uncertainty. Yeah? That's called the uncertainty, U. Is this okay? You look very unhappy, Matt. No, you can be unhappy. You don't have to be happy. Are you sure? Okay, fine. Alright, so I'll just wait a minute to let you write these notes down. Sorry, my handwriting is terrible. If you can't read a word, just tell me and I can read it to you. What the heck? Best estimate. Okay, have you got that? I can continue. Are you sure, Matt? Yeah? Okay. So basically what we're trying to do is this. We're trying to say the true value we think will be less than our average, or well, I won't say average, I'll say our estimate plus the uncertainty, and it should be more than the estimate minus the uncertainty. It should be in between the two. Okay, so if I say the person's height is 1.81 plus or minus 0.01 meters, what am I saying? I'm saying I think their height is 1.81, but I could be wrong by this much. That's what you're saying. So this is the estimate, and this is the uncertainty. Now, we need to get a balance right for calculating the uncertainty. So for example, if I was to say the uncertainty is plus or minus 0.00 meters, I'd probably be wrong. I mean, it's very unlikely that I got lucky and I was exactly right, okay? So I'd be 100% wrong, I think. But if I said something silly like, oh, their height is plus or minus 2 meters, that's a bit silly, isn't it? Their height is 1.81 plus or minus 2 meters. Well, I'm going to be 100% right, but that's not very useful. You know, if somebody said, how tall is he? And I said, he's between 0 and 4 meters. Is that really useful? It's not. So we need to get a balance between being 100% wrong and 100% right. And it's different for each course. So for this course, we try to be about 70% right. So we don't want this to be too big and we don't want it to be too small. We try to be right 70% of the time. So it's better than 50%. So that's what we call our confidence. We try to be 70% confident with our result. Some classes use 95%, some use 99%. It really depends on what you're studying. So if you're doing medicine, then you want to be 99% confident. If you're doing a physics experiment where you're just calculating the value of G, who cares if you get it a little wrong? It's not going to kill anyone. You know, so for this level of physics, we're 70% confident. We'll try to be. Okay, so now I'm going to give you some formulas. If I can, well, you can let me know if I can scroll down. Can I scroll down? I need a minute. So did Lorraine give you any ways of calculating the error? You sound so confident in that answer. Would you remember any of the ways?
It was too long.
Yeah, too long ago, was it? Or too long to do?
Yeah.
Yeah.
She just wrote the whiteboard.
Copy, good, okay. We'll try to understand a little bit today, okay? I'm going to give you 4 ways to calculate the uncertainty. And can I scroll down, Cho?
Mm-hmm.
Yeah? Okay. Are you sure?
Sure.
Okay. So I'm going to give you 4 methods. And here's the thing. Method 4, I kind of picture it like this. Method 0 is the worst method. You don't have to draw this. Method 0 is the worst method. Then method 1 is better. Then method 2. And then method 3, and so on and so on, okay? So for this level, I'm going to give you 4 methods. Okay, let's have a look at each. Method 0. So if you want to calculate the uncertainty of something, one way to do it is you just guess it. So you can see why this is the worst method. Now, the time that it's right to use this is if you have not much information, if you have no information. So like, for example, suppose somebody said, oh, I measured whatever, a student's height, and it was 1.61 meters, and they didn't tell you the uncertainty. So the only way to know the uncertainty here is to guess it. So what do you think might be a good guess? Well, you don't know. It depends if you think the person is good at measuring or not. You know. So this method, of course, is a very bad method, but it's actually okay in physics sometimes to do this if you have no information. Sometimes you have so little information you just have to guess. So that's method 0. So that's no good. Now, on to method 1, the first real method. Can I scroll down? Do you want to write this first, method 0? It's just to guess it. Okay? Yeah? Right, now method 1. So again, method 1 works when you have a little more information. So what this method is, you say the uncertainty is half the smallest measurement possible. So what I mean by that is, suppose you're measuring someone's weight. So you have here, you're measuring someone's weight. And let's say that it says their weight is, whatever, 90.1 kilograms. And then they step off, and then they step back on, it still says 90.1. And they step off, they step back on, it still says 90.1. Is their weight exactly 90.1? It's not, because the machine can't go more accurate than 1 decimal place. I mean, their weight could be 90.12, 90.11. So here you say the uncertainty is half the smallest value. What is the smallest measurement this machine could make? What's the smallest mass it could make? And you have 1, 2, dot, and another number on the screen. Yeah, 0.1. So half of that would be 0.05. Okay, so you would say his mass is 90.1 plus or minus 0.05 kilograms. Did you do that? I think maybe you did this with Lorraine, this rule, or not? No? You haven't done this with Lorraine. Okay, so this is new. Okay, can I go on to the next method? Right. Oh, Chow, do you have this?
Yep.
Okay, method 2. this method works when you measure something twice. So the example, do you remember when I showed you the experiments last week, I said when you swing the pendulum, you should do it twice. Or when you measure the angle, you should measure the minimum and the maximum. So you have two measurements. So if you measure twice and you get two values, let's call them x min and x max. So of course one of the values will be bigger than the other. And it's really not possible for them to both be the same. They could, I suppose. Then the uncertainty is x max minus x min over 2. I'll give you an example. So suppose you let the pendulum swing 10 times, and you get, the first time you do it, it took 19.6 seconds. And then the second time you did it, it took 19.6, this is 60, and we'll say this is 5. Okay. What is the minimum value here? It's 19.6. I know it looks like 19.6, but it might be better to think of it as the minimum possible value is 19.595, because that could round up to make 0.6. And what's the biggest value here? What would I say it is? 19.655. Or if you want to be particular, it would be like 4999. Because that would round up to, sorry, that would round down to this. Yeah? I'll just call it 5. So the uncertainty here would be 19.655 minus 19.595 over 2. Does anyone have their calculator handy? Mark, do you mind typing that in and see what we get?
So
0.03 seconds is the uncertainty. Who's calling me? Who the heck is calling me? Ugh. Everybody's sick and cold and tired. Yeah. Sick, tired, cold, no contact lenses. Alright. Can I scroll down to the last method? Yeah. So the fourth method, method 3. Now this works when you have many measurements. So maybe you have like x1, x2, x3, x4, ... Maybe you measure something 10 times, whatever, n. This is the best situation, right? Because you've measured so many times. So the uncertainty is equal to the sum of the difference between your data and the average. Have you seen this symbol before? This means average. Okay. And does anybody know what these bars mean? Positive only. Yeah, good. So let's take an example. Suppose I have 3 numbers. Let's say 0.11, 0.10, 0.12 meters, and I want the values here. What's the average? The average is 0.11 plus 0.1 plus 0.12 over 3, which is 0.11 meters. Okay. The uncertainty is the difference between this and the average. So how different are these? 0. How different are these? 0.01. And how different are these two? 0.01. Then what you do is you add them up and divide by 3. So that would be 0.0067 meters. So the answer is this plus or minus this is equal to 0.11 plus or minus 0.0067 meters. Okay. Of course, this is the best method. But there are more methods. But this is all we need for now. Okay, continue. No, I see chart writing. What class did you have today so far? Did you have chemistry and maths? Maths? Why is everybody so tired? Just because it's Monday? Yeah. Ready, Chow? No problem. It gives my sleepy students a chance to rest for a minute. Okay. Can I scroll down? Okay. So, I know you did this with Lorraine for sure. Suppose we're measuring something like area. Then we have two measurements, x and y. Or suppose you're measuring a person's height, but you only have a 1 meter stick. So you measure their height by measuring twice, two different heights. So 1 meter and a bit. Okay. Or what's another example of two measurements? Is anything you did in chemistry where you have to measure two different things and combine the results? Do you know what I mean? No? Okay, well I'll give you an example. Like maybe, I don't even know. I don't know any chemistry. Maybe you have to measure the volume of volume A, and then maybe you have to measure the volume of volume B, and you have to add them together, as an example. Okay, so this is how we're combining measurements. So because the measurements get combined, it means the uncertainties get combined. And how do they get combined? Well, here's the rules. So x means the first measure. X means measurement of one thing, and y is the measurement of another thing. Okay, so in my picture here, for example, x could be this direction and y could be this, or x could be this and y could be this. It's two different things. Okay, they're two different things. So let's say you want to calculate z, and z is x plus y, and you know the uncertainty of x and you know the uncertainty of y. You want to know what's the uncertainty of z. So the rule is this. This one's quite simple. The uncertainty of z is the uncertainty of x plus the uncertainty of y. So I'll just give you a small example. If I said x was 1 meter plus or minus 1 centimeter, and y was, let's say, 2 meters plus or minus 1 centimeter, what would be z? Z would be 3 meters, yeah, plus or minus 2 centimeters. Makes sense? That's obvious, I think. So that's the first rule. If you want to write that down, please. Rule 1. Okay, you got that? Now, the second rule. Let's say z is the difference, x minus y. What would you think the uncertainty is here? What do we think? Don't be shy, we're all friends. I won't tell Lorraine if you get it wrong, I promise. Very good. ux plus uy still. Sorry, Matt, did you do these rules with Lorraine? No, okay. Or maybe you did, but you... No, you were right the first time. Plus. Yeah, it is plus. Now you're not sure. It's plus, correct.
Oh, what is it?
But you told me it was plus.
No, I thought you was minus.
Ah, okay. It's plus. Because if you have some error here and you have some error here, the errors don't cancel, they just become worse. In other words, errors when they combine, they can only ever become worse, they can't become better. Okay. Rule 3. Suppose z is equal to x multiply y. What's the uncertainty of z now? So that is equal to the average value of z, so whatever z's average value is, square root. Now, you must have done this one with Lorraine. You must have. Uncertainty in x over the average of x squared plus the uncertainty in y over the average of y squared. Right? I mean, because I saw the science students had this formula in their notes.
Yes, we just copied.
Okay. Did you know what you were copying?
No.
Okay.
We just like,
We didn't see it in formula before.
Oh, really? Just fill in the blanks. Do you at least have some understanding of what we're doing today? A little understanding. Not complete is okay, just a little is good. 4. Z equals x over y, and uz is going to be the same. Same formula. Ux over x squared plus uy over y squared. It's the same formula. Okay, got that? The next one is if you have powers. Let's say z equals, let's say z equals x power n, y power m. How did the uncertainties combine here? As follows. uz equals z bar root n, isn't it? Yeah. mux over x bar squared plus muy over y bar squared. Six, the last one. The last one is z is equal to some constant times x. The uncertainty in z is just going to be the constant times the uncertainty in x. Yeah. I want to do a couple of examples with you just to make sure you got these formulas. Can I scroll down a bit? So look, here's a rectangle. And let's say we measure this side to be 1.4 plus or minus 0.01 meters. And this side is 0.7 plus or minus 0.01 meters. And my question is, what is the area and what is the uncertainty? So I want to know, what do you think the area is and what could be your mistake? Yeah? So which formula do we need to use for this problem? Which number? Number 3. We can use number 3 here. Yeah? In the last table, in the last table, the third one. No? Well, maybe not. Is it this your number 3? XY. What did you write? Oh, you wrote this one twice? Okay. Right. I want the area and I want the uncertainty in the area. I'll give you a minute to calculate. Okay. Do we have an answer? Siva? No, well, what did you get for the area? 0.98 meters squared. Okay. Let's calculate the uncertainty. So the formula is the uncertainty in the area equals Z. What is the thing we're measuring here? It's the area. That's like the Z. So that's 0.98 square root. What's the uncertainty in the x? It's 0.01 over x, which is 1.4, squared, plus 0.01 over 0.7 squared. So you see, this is like the x, this is the uncertainty of the x, this is like the y, this is the uncertainty of the y, and this is like the z, and I'm looking for the uncertainty of the z. So what did we get here for it? 0.014 meters squared. So the area is 0.98 plus or minus 0.014 meters squared. Oh, Matt. I'll trust those two. What did you get? 0.01156. Okay. Yeah? You can't get it. Did you type this in? What happened? You guys are sure you got this? You both got the same answer. Oh, Matt, this isn't. Chow, can you type this in, please? What did you do wrong?
No, because this calculator they use step by step.
Yeah.
So the calculator rounds up, so
Oh.
a bit.
Oh, okay. Yeah, grounded. Okay, can I scroll down?
Mm-hmm.
Okay. Right. You remember the triangle VIOR? Yeah? So for example, I would equal V over R, for example. So suppose I tell you that the voltage, you measured it, maybe you measured the voltage to be 2.1 volts, plus or minus 0.05 volts. And maybe you measured the resistance, for example, let's just say that's 3 ohms, plus or minus 0.1 ohm. My question is, what is the I, and then what is the uncertainty in measuring I? So which formula will you need here? 4, yeah, okay, give this a try now. Let's see if we can get this. Huh? I think so too, Matt. I think you need like one of those Casio ones. Okay. How are we doing here? Did you get the I? What's the I? The I is V over R. What's that? 0 point exact? That's a total accident. 0.7 amps. And what about the uncertainty in the I?
Oh. Final answer, 0.0287.
0.0287. That seems believable. So you must have wrote down 0.7 square root 0.05 over 2.1 squared plus 0.1 over 3 squared. Is that what you did? Yeah, good. And you got 0.0287 amps.
287.
Yeah. So that means the current is 0.7 plus or minus 0.0287 amps. Are we getting a good feeling for this? We get the idea? The reason I'm doing this is because, you know, you have your labs this week. I think we'll do them on Friday. So you'll need to do these calculations in your lab book, your notebook. Yeah. Yeah. Tough, isn't it? Okay. But I don't think they're too difficult. I know Lorraine's one was quite difficult. There was lots of calculations to do, but I think this is okay. Now, we want to practice some of these, okay? So if you go to page 178, 178. Okay, you got 178 there? Yeah? There should be 8 questions, yeah? Okay. I think what we'll do this afternoon is I'll give you, what time we got? Yeah, 10 minutes should be enough time to do these. And then I want to do all the answers with you to make sure you got them right. And do you have your laptops with you? No, probably not. No. You have yours, but none of you... No. So we'll do something else, but for the next physics class, I need your laptop because I'm going to show you how to use Excel for your calculations, okay? Is physics tomorrow? No, Wednesday, isn't it? Yeah, okay. If you can bring your laptop. Alright, 10 minutes please. Try those 8 questions there.